Well, now that we have an enhanced awareness of the strange nature of space and time, we're ready to discuss the reality of the black hole, which really amounts to the two key features are the idea of the singularity and the event horizon. So here's a model of the black hole. And when a neutron star finds itself being greater than 3 solar masses, that star plummets in onto itself, overcoming the unimaginably strong repulsive force of degeneracy pressure, neutron degeneracy pressure. But it plummets in, breaking through that barrier, disassembling the neutrons, becoming a black hole as it shrinks to the Schwarzschild radius, RS, shown here. So this is the Schwarzschild radius. And that radius is given by this formula. 2 times the universal gravitation constant times the mass of the black hole itself divided by the speed of light squared. There's the formula for the size. The black hole then disappears when it right through its event horizon and compresses on down to what we call a singularity. And nothing, not even light, can escape from inside the event horizon. Given that that's the case, that has huge implications for what we can know about the black hole. It has the full gravitational effect of its mass. So a black hole is primarily observable through its gravitational influence on the surrounding region of space. But because electromagnetic radiation cannot escape from the event horizon, the appearance, the external appearance of the black hole tells us nothing about what's inside of it, because photons cannot emerge from it and inform us about what's inside. Interestingly, the magnetic field that it might have had, which it almost certainly did have, typically huge magnetic fields, is eliminated as well, radiating away as electromagnetic radiation when it's outside the event horizon. And any magnetic field that might have persisted is now dissipated or radiated away as gravitational waves. Well, there's mystery, lots of mystery here still. So the mystery of the singularity is that it's often assumed to be of infinite mass and zero volume. Zero volume and infinite density? That's really a strange idea, and it's easy to say and it sounds palatable enough. But really, we don't know what it is. And I want to make a significant point here just to say that if you hear some erudite scientists waxing eloquent about the Big Bang singularity being an entity of zero volume and infinite density, recognize that that's a statement of ignorance. And that scientists should not be saying that, because there is not a person on the face of the earth that knows what the singularity really is, other than it's incredibly small and incredibly dense. The reason we don't know is because we need a theory of quantum gravity, and we do not have one, because it includes the physics of the very small, which is quantum mechanics, and the physics of huge mass affecting space-time, warping space, that's general relativity. And these two theories, which independently are very well established and understood with strong predictive power, they are divergent theories. They don't predict the same thing. They don't come together. So this is a very uncomfortable reality that we're faced with, is that we don't know. Nobody on the face of the earth knows how to bring these two theories together into one, but we know for a fact that they do come together. We're just too stupid at this point in time to be able to describe exactly how that happens. So, well, that's in a way it's a happy tension, because there's lots to learn. I'm just kind of hoping that the human species gets to the point where we can actually break through this barrier, because it will be an awesome increase in our understanding of what's really going on with physical reality. So it's an imagined point in space-time. Imagined point in space-time. Because a point is a spatial size of zero. All right? And has an imagined infinite space-time curvature. Being of infinite density, then space-time is curved infinitely around it. also imagine infinite gravitational pull because you're essentially zero distance away from it. So the pull goes to infinity. So again, these are ideas that are predicted by general relativity, but we know that general relativity is not the whole story because quantum mechanics has to be consistent with it as well. The fact is the laws of physics break down as we understand them, and so we have to just keep that in mind and be a little bit humble as we discuss what we think we know about this singularity. But the black hole is specified by mass, electric charge, and angular momentum. It's a really simple entity. Moreover, it's likely that because they're a large, massive object, they don't have any net electric charge. So then it's just mass and angular momentum. And there are two different types. There are rotating black holes and non-rotating black holes. So it is to those two basic types that we now turn our attention briefly. Once again, the black hole is a very simple entity so far as we know. The simplicity is somewhat forced upon it because once you have an event horizon, then information doesn't come out of it. There's no way to tell if that black hole is made from Twinkies or from houses or from rocks or anything else. Well, there's the non-rotating or Schwarzschild black hole, and this is really simple with a singularity and an event horizon. So general relativity then predicts that all the mass compresses to an infinitely dense point, the singularity, but as we just discussed, we know that's false because it's not consistent. General relativity and quantum mechanics are not consistent with each other. So then there's empty space from the singularity out to the event horizon. Nothing really there of any import. The rotating or Kerr black hole is just a little different. In this case, if we have non-zero angular momentum, we end up with the singularity not just being a point, but an infinitely thin ring rotating about. So the singularity becomes a ring-shaped structure. Right. And we would predict that just as, the ice skater bringing her arms in spins up, a supergiant star collapses into a neutron star, spins up like crazy. Well, this should spin up even more because the mass is being pulled in ever more than it was with a neutron star. And so we would expect thousands of rotations per second being the rotation rate of these black holes. The ergo region is a strange little place where space itself is being dragged, and you can't have an object being at rest in this region without slamming into the black hole. So it's got unique characteristics, but can be understood kind of intuitively by thinking of whipping up some chocolate. So we're spinning the chocolate in some kind of bowl, and we have the black hole and the event horizon here with the chocolate being the space around it that's being drug along with the spinning black hole itself. So that's a way to visualize a spinning black hole. I spent a lot of time on this slide, but I thought it was worth it because I really needed you to have a deep appreciation of my understanding of what a black hole really is. Just to give you a little more insight into the size of various black holes, less than stellar mass, or any black hole for that matter, we have the Schwarzschild radius, which is the radius that if an object achieves, it will by definition be a black hole. And that radius is twice the universal gravitation constant times its mass divided by the speed of light squared. Here is a computer simulation of a black hole. And if we have a photon that finds itself right at the event horizon, or just inside actually, it will be trapped and go to the singularity. The photon that's just outside of the event horizon can escape. That's why we can see light outside of the event horizon. So that's a pretty good depiction here. Any object with a radius smaller than the Schwarzschild radius will by definition be a black hole. Here are some examples. For instance, our sun If it was compressed to the Schwarzschild radius, this is what that radius would be. So we'd have a object a few miles across. Earth, about a 1 centimeter radius. So we're talking about the size of a marble. If we could compress the Earth to a marble, we'd have a black hole. Jupiter, a couple of meter radius. Well, all these objects are, this is hypothetical. None of them would actually achieve black hole status, because to make a black hole you need forces that overcome neutron degeneracy pressure, and none of these objects ever get to that point. Nevertheless, it gives you an idea about just how much compression has to happen to a given object for it to be reduced to its Schwarzschild radius. Let me take one more stab at the idea of the curvature of space from massive objects and the idea of a gravity well. If you think about being in a well, it takes some energy to climb out. Well, the same idea can be thought of in terms of any object like the Earth. If you try and climb out of the gravitational field of Earth, say you have an infinitely high ladder. As you begin to climb, it's hardest at first, but as you get higher up the ladder, the gravity of Earth diminishes and it gets easier to climb. But it takes a certain amount of energy to ultimately escape that gravitational influence. Here we have a 2D rubber sheet that's really representing four-dimensional space-time, so it's highly simplified. But there's no mass to distort its curvature, so it's flat space. Now we put, let's say, a 5 solar mass star on this rubber sheet. So it's just a iron ball in our analogy or something, and it bends the rubber sheet. So you see the distortion or curvature of space. It curves space-time, and objects moving through this space-time will not just go straight, but it would be more like this. It would curve around as a result of that curved space-time. So photons and objects themselves will curve as a result of being in this distorted space-time. And that can become very extreme. If we take that 5 solar mass star and reduce it to a singularity, then this distortion of space near it becomes ever more enhanced. From a distance, the pull of gravity is the same whether the 5 solar mass star is in star form or black hole form. So you go many radii away, there's no way to tell whether it's a black hole or an actual star other than the light it's radiating. But this all changes radically, of course, when you get really close and then when you pass through the event horizon of a black hole itself. So this changes a lot. Notice the curvature becomes much greater. See the relative spacing between these space lines here. The geometry is altered, and notice the spacing becomes highly stretched. So we're stretching space dramatically. And as far as energy, this becomes a bottomless pit in terms of a gravitational well. It goes very deep. In fact, we often think of it as going to infinity. And if you're caught down deep inside this well, the cry for help is fading into oblivion because you are so deep down inside that no amount of energy could ever enable you to climb out of this well. It would take an infinite amount of energy, which is why you can never escape the event horizon of a black hole. Black holes are really strange objects, and their effects on space and time are almost beyond belief. Well, for that matter, a lot of people don't believe their effects, which can be measured, but it's just so contrary to our common experience that it's just very difficult for us to embrace it. Well, it's just science, and its effects on time are very great. Now, this lovely equation, I'm sure you'll agree it's lovely, right? Demonstrates that according to a distant observer, that time actually stops at the event horizon. It literally comes to a stop. So a friend of yours carrying a clock toward the event horizon, that clock will stop ticking as they approach, which also means that you will never see your friend enter the event horizon. they'll never enter the black hole from your point of view. From their point of view, they have entered the black hole without any trouble, although they have plenty of trouble because it is not healthy at all for you, as we'll see in the next slide. Gravitational redshift is another reality that we alluded to. All wavelengths of emission near the event horizon are redshifted. They're shifted to longer wavelengths. Frequencies are lowered. So here's a high energy photon trying to escape the event horizon, and it's just trying so hard, but it can't make it as it shifts from violet to blue to green to yellow to orange to red. And that photon is so stretched, its energy goes down. So it's dimmer because the energy of a photon is inversely related to the wavelength. The wavelength is increased, and so its energy goes down as well. It's stretched so much that it actually disappears from existence. You can't slow a photon down. It's always moving at the speed of light in any reference frame, as we discussed before. But it can evaporate from existence, and that's in fact exactly what it does. So here we show you're being brave and orbiting a black hole, but your friend is a little bit more brave, and they ease in a little closer, hopefully not so close that the rocket engines can't get them away. But notice your digital blue clock recording 50 seconds of time having transpired. Your friend over here, his clock is redshifted, and only 15 seconds has gone by. It gets a little bit too close, the same process would approach zero time. So that is the reality and some of the very strange phenomena of black holes. But there is more strangeness, and this gets very personal. It's called spaghettification. You can visualize spaghetti right now, right? Well, go ahead and keep that in mind. If you're falling into a black hole, it's not going to be a very good day because you will get stretched. Now, from an outside view, you never make it. From an outside view, time stops. So putting that aside, if it's you falling in, you will make it. In your reference frame, time is such that it's happening for you. And you're going toward the black hole. Now keep in mind that this has got a very strong gravitational field. And through the inverse square law, your feet are significantly closer than your head. So it's kind of back to medieval days. You're on a rack and you're being stretched. Your feet are being pulled harder than your head. Well, the traveler, we'll call it you in this case, you get stretched and you get compressed. Because based on the direction that these forces are acting, they're kind of at an angle as you get close. It's smashing you together as well. So there's frictional heating. And if you ever find yourself emitting X-rays and gamma rays, that means you've been heated to millions of degrees, and it's not a good day for you. You have passed the black hole event horizon, if you ever do. You're irresistibly drawn into the singularity. There is no force in nature that can draw you out. But unfortunately, the stretching part is a little more extreme than any medieval torture machine. It not only pulls your feet off, it pulls every cell of your body apart. Then it takes the cells and stretches them to the point where they're split into their constituent molecules. The molecules are split into their atoms, and the atoms are dematerialized in their subatomic components. So it's a fairly complete process of spaghettification. You are stretched to the ultimate.